And then let me add the text. Now we have slightly, not slightly, it's kind of difficult part, but to exploit something called the Euler equation. In finance, in actually economics, you have important concept called Euler equation. Euler equation is basically first order condition in optimization problem. First order condition that you learned in the mathematical economics class in the first year. And something called martingale property. Well, this is a different concept. You can Google it. Of Ford price, we get, okay. Instead of very rigorous explanation, I'll give you just intuitive explanation. So, given if everyone optimizes their decision in economy, then what we have is zero should be T of expectation, okay? And then expectation of what? Should be zero. Expectation of change of forward rate, intuitively change of forward rate is zero, but the price of the change forward rate should be zero, actually. Okay, they are too close. Let me put comma dot here. Okay, this looks pretty. Well, the intuition of forward rate is basically the promise of each other, right? When we make forward rate, when we make a forward rate contract, that we just determine the forward price. Okay, today is a small t, but at big T, let's make the value of a contract that we receive $1 at big T plus delta as big F thing. Okay, so today we don't exchange. Today we do not exchange cash, right? To make forward contract, right? Therefore, the change of the price of the change of the forward contract, i.e., let's make it four, let's make it simpler, i.e., df price should be zero because we don't exchange cash. All right, that's the meaning of this one. Since for the contract, this is just promise of two parts that they promise each other that at some time in the future at big T, they promise they'll exchange cash at that time. But today they just make promise with each other. They just exchange words, not money. They exchange money at big T. So the change of this promise from today to tomorrow, that should be also zero. The price of the change of promise between today and tomorrow should be zero because we also know tomorrow there is no cash flow, right? That's the intuition of this one. So change the price of change of the forward contract from today to tomorrow should be zero. Okay. And then since we know price of the forward price, so we can rewrite this one as Okay, rewrite long left right arrow. Then we have long left right arrow. And then, okay, this one is basically meaningless. Ah, let me put 0 over here. Uh, they are basically same. They are meaningless, but because we know price for the price that we determine today, which is constant, it is known information. So by we can divide f t over here, right? Same because of ft is known, all right? All right. Then, well, then we have something like we have something like so. Okay, they are of course the same, but here, okay, so well, to make it very easy, okay, dt, and then we have this one, right? Okay, so I have one step. Okay, I jump one step. So, so here this is the I make one step jump. So, right? Well, basically, this is the change of df. So we divided ft plus dt and this one, right? So this is basically 1 over here. And then this price of 1 is risk-free rate, right? Here we have this part. To use this one, to price 1 the risk-free rate, what we can have is we can move this one over here. Okay, this part over here, then, okay, okay, same, but we can move this one part, okay, so this is 1, so this one part is over here, so we use this one, okay, and then I copy this part, okay, and then so I made a slight jump like this, okay, is it okay? So can you follow me? Is everything okay? And then what we can do is this one is now by the definition of the fourth rate. So basically this is same to ET of MT plus DT, okay, multiplied by, and this term is the change of, basically change of the fourth rate. Change of the fourth rate. Okay, so well, in make we can write it this way, right? Because the ratio, so we can take log exponential, then you can easily show that it is basically change of fourth rate over here. Okay, of course, to make it more rigorous, I can put subscript t over here. Okay. Okay. So is everything okay? I know it is. I know it is a bit difficult. I know it is a bit difficult. I can fully understand it. Okay. Let's make a new text over here. Okay. And then this part, the M part. Okay. This M is looks like this. So I put this part. Okay. We know M looks like this one. And then let me change this one to the E. Right? They are same. Okay. And then we multiply this one. So this is M. So we use this one. So because this is M. Pricing color. This is the pricing color. Okay. Pricing color. And then we multiply this one. And then here we multiply this one. Okay. And then if we take expectation of it, okay, given this notation, okay, let me put C dot over here. C dot. Okay. So this M looks like this. So and then take expectation of it, as the equation shows. Take the expectation. Okay. If we take expectation, then this one should be the discount rate, right? Value of contract pays $1 at small dt times later. Okay. So this is same to this one. Okay. Now we have a very convenient one. We have this RT over here, RT over here, so they cancels out, right? So we can basically cancel out this part and this part. This is very, very convenient, right? So basically what we can do is we can cancel this out, right? So this part is, we can pick this part outside of expectation because there is nothing stochastic about it. There is nothing stochastic about it, right? So therefore, well, I can copy and then divide each side with this one. Then this part goes away, and this part becomes 1, right? Look at this one. And then moreover, we can combine this together. So this is exponential and exponential, right? So, well, why do we need this one, right? You can put this together, right? This is exponential and exponential. So we connect them, and then this is small. So let's say exp. So looks like this. Okay. Okay. So next thing is we can use the Ethoslemma. Using Ethoslemma, we can solve this one, and then we can get rid of exponential term. That's the next step. Using Ethoslemma, okay. Using Ethoslemma, we can solve this one and remove this exponential part. Okay, that's something we wanna do. Okay. And then here, and then the question is, of course, how can we remove this one? Now we have exponential part, but here first we need some notations. We have to introduce some notations. Okay, so to introduce some notations over here, what we can do is first we need the we need the variance of this part, basically. Variance of this part. Okay, so it is here. It is for some particular fold, right? Particular fold, right? So variance of this part. So let's put n over here. For each, this should hold for each fold, right? Each fold, right? And then to introduce notations over here, to introduce notation, okay? So let's say to use notations as follows, okay? Here, sigma, okay? Sigma, and then because it's fold rate, and nth fold rate at time t in the square, okay? Fold rate. We denote this one as the df and t square. Okay, and then to make it time independent, let's add dt over here. So these are notation, but this is notation, not equation, not equal. It is equivalent actually. because it is the notation. Actually, let me make it center. One more dot over here, and then send it to center. Okay, notation. And then covariance, the covariance between the ZZ and then TF. Basically covariance. Okay, covariance between the digiton the Z nu T, because this is source of risk, right? The risk stochastic, and then covariance this one, and then this one, DF and T. So we have a K source of risk, and then we have one fold, right? So this covariance is because it's covariance factor with K number of the length is K. Okay. And then this covariance, and then if we divide this one with with oops divided this one, actually before doing this one, I want to divide this one first to make it easier. So if we do this one, this is called basically, I'm not sure you remember this one, basically this is basically regression, because denominator is covariance and numerator is basically square of this f term. So this is basically called regression coefficient. Basically regression coefficient. Regression coefficient. Yes, so that term is called regression coefficient. And then I denote this one as, since it is regression coefficient, so I call it beta, because regression coefficient, I usually call it as a beta, right? But because it is vector, so I put vector over it. So yeah, vector of beta, because covariance is a vector. And then it is the vector, it is a regressing curve. We are basically regressing the source of risk onto nth fold rate, change of nth fold rate at time t. So I can put nt over here, subscript. Nt over here. So we have this one. Okay. And then because we already use this notation, so what we can do is actually instead of df square, I can use this one. Okay. If I can use this one, okay. If I put this one, because it's divided by, okay. So now if we put this one, basically, okay. Now we have no dt, so basically we are multiplying dt each other. So here I multiply dt. Okay, so this covariance term, regression coefficient, time independent. So this gives us a hint. It gives us a hint how we can estimate this entire model. Okay, because it's regression coefficient. So basically, what we can do is we can regress shock to the change of the fold rate. Then we can calculate beta. Okay, this is like a huge tip to estimate model. Very powerful tip. So again, it is equivalent. Now, okay, very powerful tip to estimate model. So therefore, it is basically, this is basically I regression coefficient. Basically, this is regression coefficients. Okay, so this is give us great tip about how to estimate the model. Okay, yes, I know it is a bit difficult, but let's slightly continue more. Okay, then okay, then if we use Ethoslemma, okay, then again this is too long, so well now by using this one, I can solve this exponential part using Ethoslemma. So I using let me text, and then okay. So here what we can do is, okay, basically we can get rid of exponential. So what we can do is here, okay, let me copy this one, okay, let me copy this one, okay, and then this one is basically it is obviously exponential of the 0, right? Well, this is not pretty. Yeah. Exponential of 0 is 1, as you know. Yeah. Okay, and then we can remove this one by Ethoslemma. So this one is basically this one, and then first, happily, now I want to remove exponential term. Okay, but I cannot simply remove exponential right now because there are some convexity adjustments. So this one convexity term happily goes away. It is all called Ethoslemma. This convexity term goes away. Okay, and then we can think of this as stochastic part only, stochastic part, and then we have this squared term. We have a squared term of this one, and a squared term of this one, and covariance term of these two. Okay, something we can calculate. So the covariance of these two is we can because it is a this we have this beta part. Okay, so what we can do is this one, and then include basically square of the stochastic form. So I can move this one over here. And then this is minus, so it is minus minus plus. So we can express this. This is called Ethoslemma. Okay. This is called Ethoslemma. I remove exponential. Okay. And then exponential, in order to remove exponential, I use the Ethoslemma, and by using Ethoslemma, I add convex term and make it they are same. Okay, of course, I have to solve this squared term. And then because this one, okay, this one negative, and then this is the change of address. So let me move this one over here. Okay, move over here. Now this is simply 1. So actually, I made one step. So actually, yeah. So there should be plus 1 over here, but plus 1 and this one cancels each out. So and that this one 0, and then I move this one. Okay. So okay. Yeah. Yeah. So okay. I jumped one step, but let me show you step by step again. And then I have to write down this one again then. Okay. Okay, we have this part. So because exponential is 1 plus something. So basically we have this one. So Ethoslemma. Okay. So this step is Ethoslemma. Okay. So by applying the Ethoslemma, yeah, by applying Ethoslemma from here, by applying Ethoslemma over here. But this is also 1, right? Actually, yeah. So yeah, this is 1. Let me just write down this as 1. Okay. So this is 1 over here, 1 over, this cancels each other, and then cancels each other. So cancel each other, and the df part over here. So yeah, and then right arrow. Right. So yeah, now there is no jump. Okay. Now there is no jump. Okay. No, 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 no. No, actually, I need this one. Sorry. No. Actually, this term doesn't go away yet. Okay, it goes away after I solve for square term. Okay, so like this. And then one thing is that now we have to square of this term. Okay, where is dt? Square of the dt over here. Now we have square of the dt over here. Okay, we have something like this. Now I don't have any missing terms. No, there is a long dt. Yeah. There will be dt over here. Okay. Ethoslemma. So I can solve. Okay, this is square term. If I solve this square term now, well, let me remove this one, and then let me add another text, and then let me copy the rest part, and over here, okay. Now I solve this squared term, okay, squared term, first squared term is basically this first squared term is the same to this one. So the first term is basically by Ethoslemma, this one same to this one. Okay. So and then I have the square of this term, but we know what is this one. It is basically to use this notation, basically we have wait, I missed something. Yeah, this here we have a big delta over here, but I miss big delta over here. Okay, so this is always easy to make mistake. Okay, now I have a delta over here, delta over here, delta over here. Okay, so I squared of the distance, and then square of the distance I use this notation. So this plus sigma of the f and t square over 2, right? Square over 2. But we have this this delta term, delta square. Okay, with this term. So this term is now addressed. Okay. Now the most interesting part. Now it's equal to 2, this one, right? But now because, well, we have covariance term over here, so it is square. So this interesting part is 2 multiply of this one and then sigma. So this one is and then we multiply 2. This is a plus b square term in some sense. Then we have 2ab, right? But we divided by 2, so we have a multiplied b, only that part. So we have lambda prime okay. And then we have now the beta back beta nt, right? Well, someone is making noise. Okay. Please mute yourself. Okay. Yeah. Beta. Okay. And then of course we need dt. because we have dt term over here. And then we have delta over here, right? So we have to multiply this delta. Wow, this is become very long. Okay. Because we are multiplying each other, this one and this one is a beta dt. And then, right, beta dt and then sigma square, okay? So, and then we have to sigma square f and t, okay? Wow, this is so long. Yeah. You know, if you do the final, sometimes you have to solve this long equation. This happens. Okay, so let me check. This one will multiply this one to this one and this one. This one is beta dt sigma, so beta dt sigma square, and we have delta over here, lambda. Okay, now everything looks perfect. But now we have this lambda over here, lambda over here, so they cancel each other, right? So we can significantly, right, simplify this one by removing this one. Okay, so we have this one. Okay, moreover, another interesting part is, well, we have a dt term everywhere. Actually, yeah, actually, this one sigma is over here. So yeah, I miss dt term over here. Yeah, of course we need a dt over here, right? And then yeah, we have a dt over here. We have a dt term and then sigma over here, so we can put this one outside. And then we also have a delta. Okay, so I move this one over here. Okay, so same. And then I put parentheses using I put sigma square, over here, and then sigma square, over here. So first, what we do is I first put sigma square out of this one, then we have a sigma square dt, and then we have this one, right? And then we have this uninteresting dt delta part. So we remove this uninteresting delta dt part over here, and then we can remove, okay, one delta over here, dt over here, and then we remove dt and delta. Okay, all right. Why are doing this? Now we have a final equation. Now we have ET part both sides. So if we remove this expectation part, then we have noise, right? We have noise. So by removing exponential part, So finally, our empirical equation becomes now I remove this one. Okay, equal this one. So this one, but because we need expectation part, so we have a error term. We need a term. Error term something independent of everything else. Okay, independent everything else, and then we can add some dz and error, some error term over here, independent everything else. But because it's standard Brownian motion, so we have sigma and to scale up some variance, and then, well, as we have more and more gap between the data, we have higher likelihood, higher error, so we can add a delta over here. Now, we have a final empirical equation. So basically, now we can use this one. In some sense, we can also use this one because we can observe change of the, we have the change of the forward rate, and the lambda is something we want to calculate. Okay, this one is standard. We can estimate beta regression coefficient. So basically, using this equation, we can basically calculate lambda. Calculator from data, we can calculate lambda, which is basically here we model new zero and new t. So well, we can estimate more in the sense, right? So right. So here lambda t is right. Lambda looks like this. Bar is over here, over here. So we have this delta everywhere. So now we can remove delta. Okay. So yeah, if we have a very small data, we can even get rid of this one. But by now, and then therefore on empirical design becomes this part. Okay. So basically we can use this equation. Now we have equation, and we don't know this new zero and new one. Okay. Everything else is, or we can either calculate or observe. Okay. So we have another lambda t over here. So why we have a lambda? Why do I miss t over here? And then okay. And then this is the, I can put delta over here, 1, and then Yeah, something like this. So if delta is very small, if the delta is very small, or our empirical design would be, our empirical design becomes, well, we can even remove this entire part. So we have now very convenient, yeah. In some sense. Yeah, maybe too short. In some sense, maybe too short. Only when this is very small, right? We are extremely simple. So we can basically calculate with basically some OLS regression, possibly. I think this is enough for today. Do you have any question?
그 수업 대해서